a graph with many different, or 3 different temperatures on it, okay? Here's a 3000 Kelvin, a 4000 Kelvin, and a 5000 Kelvin. And you can see, again, those same things we were talking about. As the temperature goes up, the graph is always above a graph at a lower temperature at any given color, any given wavelength or frequency. It is also, move that down there, the peak is higher, of course, and the peak moves to the left in this graph, a lower wavelength or higher frequency, more towards the purple end of the spectrum. But there was a problem, okay? So this is what the experiments were showing. But people started to realize, hey, if you do the math with our theory about physics in the world, the theory says that at 5000 Kelvin, instead of the equation that they came up with using the letters and the theory and the math, instead of that theory and math following this blue line, it does decent down here, but up near here, it gets way, 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 way off, okay? Up here, the experiment has a peak and comes back down. The theory, the equation from the theory, keeps going up and up and up to like infinity, which first of all doesn't make any sense, because that would mean that at very high frequencies, like gamma rays, it'd be giving off a gazillion gamma rays. So something, even if it weren't this high of a temperature, even if it were a much lower temperature, it would come way down here, but eventually it would curve and go way, way, way up to infinity. And that doesn't make sense, because something that's, doesn't matter its temperature, whether it's hot or cold, it's not giving off an infinite amount of energy at high frequencies, like an infinite amount of gamma rays. That doesn't make any sense. Also, it didn't fit the experiments, and it doesn't even come back down. Okay, so we need to have something that goes up and then comes back down. Somebody did come up with an equation that got a little bit better, but it didn't still quite fit the experiments. It came up and it came back down, but on this side, its equation was kind of far off from the experimental results. So here's the problem. The problem was that classical physics, using their equations, things they had already knew and discovered, they could not explain that graph, that experimental data. The theoretical equation had the intensity of light going to infinity at high frequencies, which doesn't make much sense. So the problem with this theory was dubbed means given the name, the ultraviolet catastrophe, basically saying that our whole knowledge of physics is not working at all up in the ultraviolet-ish region, where the graph comes back down here in the ultraviolet. It's going up to infinity in the ultraviolet. So that's dumb. So this equation doesn't work at all for ultraviolet. It goes off to infinity. So it got this name, the ultraviolet catastrophe, since the theory didn't show even the same shape once the light became in the ultraviolet region. Okay, so that's our problem. The theory, physics, isn't matching reality. Okay, so the physics must be wrong. So what is the right physics? And along comes Max Planck. This other guy, Wien, had come up with an equation that was decent, but Max Planck developed an equation that described the data very well. Okay, good news, right? He's got this equation, but it comes about in some weird way. In his derivation, okay, derivation is where you take formulas you already know, the physics they already knew, and put them together. He omitted, it means he took out a math step, okay, and supposed that the molecules or the atoms, he called them resonators, okay, that emitted light. So you got to realize this is before they really understand what atoms are. Electrons had, no joke, just been discovered like a few years beforehand. They had no idea about electrons. This is 1900 and I think it's 1897. We'll talk about that later, but the discovery of the electron. So he doesn't have this picture of protons, neutrons, and electrons. He just has this idea of like stuff, okay, maybe these little atoms or molecules. And he says he thinks that they're resonating. So these things are like bouncing around, okay? These little things shooting off the light. This piece of metal is made of things that are shaking and shooting off light. And he says he supposed that the molecules or resonators that emitted light could only absorb and then emit certain discrete means separate or specific amounts of energy, okay? So let me show you kind of on a paper. Okay, so here's kind of the deal. Imagine you could see these like atoms of the hot metal, okay, that's being heated up and glowing. And again, he doesn't have any idea what atoms are made of really, but just he's imagining these resonators, he's calling them. They're shaking around. Okay, so this guy is bouncing, back and forth, or something like that. He thinks it's shaking back and forth, probably with a certain frequency. Okay, and then remember what resonance is? Resonance is when something shakes. Resonance is when the frequency of something being shaken matches a frequency it likes to shake at. We talked about how standing waves on a rope are similar to, they're an example of resonance. Okay, so I think, he's thinking about these atoms or these resonators like a rope on a string. It likes to have this resonance or this resonance or this resonance, and this would be the fundamental frequency, and this would turn out to be the lowest energy, by the way. The frequency is the smallest. This, if you remember, has double the frequency, and this has triple the frequency. So this would be 3 times E1. Let's just, even forgetting, okay, something like this. He's thinking of these guys as something like this. Okay, so whatever this energy is, I'm not sure, but this has double that energy, and this has triple that energy, and the next one would have 4 times that energy and 5 times that energy. And so he's imagining this thing as it vibrates around, it can't have any vibration. It can't like shake at any frequency it wants. It has to shake at a certain frequency, okay, to kind of like, and he's not saying why, he's just saying that's what it seems like. That's what my math is telling me. Okay, this is, or what math I use to make this equation work. So these resonators can only shake at like certain frequencies or something like that. They only have certain energies is really what he's saying. These shakers only have certain energies, kind of like these standing waves have only certain frequencies and therefore only certain energies. Okay, but when he looks at the math, it might have been hard to see that. Or should I say, when he looks at the numbers, it might have been hard to see that. So look at these numbers here, okay? What do you notice they all have in common? What's the same about all of them? All right, well, if you start looking at these, right, it looks like all of them, if these were dollars, for instance, they all are an even number of quarters, right? They're all 0 cents or 75 cents or 50 cents or 25 cents, right? So it looks like, these, nobody's going by nickels or dimes or pennies, right? They're only going by quarters, right? So if I were to go like this and take this number over here and divide by 0.25, it's going to be a whole number. And actually, every time I enter an equation in here, I'm doing random numbers. It generates new numbers. But no matter what I do, these are always whole numbers. So $179 is 716 quarters. 55.25 is 221 quarters. Okay, so this number here is some integer whole number multiple of 0.25. Okay, now that's pretty easy to see because we're kind of used to, zeros and quarters and halves and, 3/4. But look at these numbers here. It's pretty hard to see a pattern in those numbers, and his numbers were much more like this. Okay, it turns out that I've set this up so that if I take this number and divide by 0.0006, it's always a whole number, no matter what numbers are over here. Okay, these numbers are all some whole number, multiple of 0.0006, because that's how I set up these numbers. Okay, with the random number generator. So his numbers were much more like this. You wouldn't look at these and be like, oh, it makes sense. It's a whole number multiple of 0.0006. You would never see it. Okay, but as he looked at his numbers, he couldn't see it either. Not because he wasn't a great mathematician, but because they didn't have enough significant figures on these numbers probably anyway. Okay, so if the significant figures are 1.32 and it's some integer multiple of 0.006, you're not going to notice really. Okay, because I don't think they had enough significant figures on their experimentation to really see that it was a whole number multiple. But in his math, he ends up saying this energy, okay, the energy of this resonator is, so I'll do energy of the resonator. In my math, I'm saying it's some whole number, and in math class, they like to put an N. This is a whole number. Actually, I'll just write whole number 1, 2, 3. It's a positive integer. 1, 2, 3, 4, dot, dot, dot. Okay? Times, and he figures out it has to do with the frequency of the light that it's being given off. So remember that blackbody radiation? We graphed wavelength. That's supposed to be a lambda for wavelength. And lambda. And intensity. And it went up like that, and then came down like that. Something, kind of like that. He's doing it based off the frequency, not off the wavelength. But they're related because the speed of light, c, is frequency times wavelength. Okay? But it's some small little piece of the frequency. It's still not it's not a whole number times the frequency. It's a whole number times the frequency times some teeny little number. And it's super duper duper small. And they named it later after him. It's called Planck's constant. Okay? So Planck is saying that the energy of these little resonators, as they shake back and forth, they can't have any old energy. They have to have an energy that's a whole number multiple of this little teeny tiny energy, which is related to the frequency. So each color has its own little teeny tiny piece. That it's like each color of light has its own little number here that you're taking a whole number and multiplying by. So going back here, in his derivation, Max Planck, took out a math step, okay? And he supposed that the molecules or the atoms, the resonators, that emitted light could only absorb and then emit certain discrete, separate, specific amounts of energy. They can't have any energy they want. They have a multiple, the energy of the resonators is some whole number multiple, some positive integer multiple of this little piece, this little amount of energy, okay? But the amount of energy is dependent on the frequency of the resonator. Actually, I said light before. I think he thought of it as the frequency of the resonator, okay? Where n is a whole number, f is the frequency of their shaking, the resonator shaking back and forth, and h is a constant that made everything work, okay? So in his math, when you take calculus, you'll learn something similar, I think, to what he did. They take things and break them into little pieces and imagine that they come in little pieces, and then they say, nah, but it's really not little pieces. Let's make the pieces get super small, infinitely small, and let's add them all up, okay? He did something like that at first, and it didn't work. When he took out imagine that the pieces get smaller and smaller and smaller till they're infinitely small, when he took that step out and he omitted that math step, he got an equation that worked, okay? So he was trying to do it a different way. It wasn't matching the experiment. He does this and puts something to do with this in his equation, and it works. Now, I'll show you the equation, but you're not going to like it. So here is his equation, all right? This is based off of the temperature, okay, T for temperature. It's a function of the temperature. 2 times his Planck's constant times the speed of light squared over the wavelength, when you put it in terms of wavelength to the 5th, times 1 over the number e, if you even know what that is, to the h times speed of light power, divided by h over c is part of the power, and the power is divided by the wavelength times kb, which is another constant, times the temperature. It looks gross, right? So not easy. You wouldn't just look at this and be like, oh, obviously that's the equation, right? But this is the equation that he derives and comes up with that matches the experimental data. So here your book has this red line is Planck's equation, what it said should happen, and the red dots are the actual data that people took from experiments. And you can see that his graph is matching the experimental data, the dots, very, very well. Okay, so they think, oh, Planck is onto something. But if this doesn't sound weird to you, it should. And it should sound weird to you because the thing that was weird was, why would these little resonators, these little atoms, whatever they are, going back and forth, why would they be like standing waves and have only certain energies? Okay, why would they have like only certain energies that they can have? Okay, that didn't seem to make sense. And even Planck himself didn't think he was right exactly. I mean, he thought his equation was right, but he thought that he basically said this: my math is working. Now, how does it fit reality? Like, how are we going to mesh our physics? I came up with new physics. How does my new physics with this, how does it mesh with our old physics? He supposed it did. He didn't think he was throwing out old physics and making new physics. He said, I came up with a new thing. Let's figure out how my formula, this thing, how does my crazy formula fit with our old physics? How are they both true? How do they fit together? It turns out we don't think that they do fit together. We think that he created something new. He didn't even know it. Okay? And the thing that he created was this idea that sometime, or actually all the time, only certain energies are allowed. Okay? And he didn't think he was saying that yet, but his equation was showing it. His equation worked only if he imagined that these resonators had only certain energies that were allowed for them. So let's wrap it up here. Blackbody radiation. Planck's mathematical model was the first idea, even though he didn't even think he was really saying this yet. It was the first idea that energy could be quantized, okay? That energy could have only certain values are allowed for the energy of something. In this case, the energy of his resonators bouncing back and forth. For some reason, his math was saying they could only have certain energies. This idea ended up leading to what we're going to call quantum mechanics, and we'll learn this later. Einstein used Planck's idea to develop a theory of quantization of energy of photons to explain something called the photoelectric effect. Okay, so Planck does his work. Einstein uses Planck's work, and we'll talk about this later, to explain another experiment. And then the famous Niels Bohr used Einstein's ideas to explain emission and absorption spectra of gases by developing a theory of the quantization of energy of electrons in atoms. So basically, Einstein uses Planck's theory to explain another experiment, and then Bohr uses Einstein's theory to come up with a model of the atom, the Bohr model of the atom. So you have to remember here, we're before the Bohr model of the atom. We don't know anything about like electrons, and them having, we don't know anything about electrons, basically. Somebody's just discovered there are such a thing as electrons. We have no model for an atom, okay? So you got to go back there with us in this history. Planck comes up with this equation that models the blackbody radiation well by saying in his math that only certain energies are allowed for these resonators, okay? But it ends up leading to this explosion in this whole new theory and realm of theory in physics. It says, but Planck used the quantization of energy as a mathematical tool. He, and no one else really until Einstein, he didn't think that energy was actually quantized. He didn't think that the resonators actually only had certain energies they could shake at. He just says, my math is working. That weird equation is working. How does it fit the old stuff? How does it fit what we already know is true? He didn't think he was coming up with something. He didn't know he was coming up with something revolutionary. Okay? So here's a question for you. How was Max Planck's model different than classical physics? So the physics that came before him. How was his model different than anything that had been said before? And did Planck think that classical physics was wrong? That his model was wrong? Or that they were both correct? Okay?